Alright, so this is part 2 of the chapter 2 practice test. I'm supposed to find the derivative. There's no instructions here, but I'm finding the derivative of this. And this is an exponential function because the x is in the exponent. And the big deal about these is you don't subtract one from the exponent when you find the derivative. So there's more or less a formula for exponential function derivatives. We do the coefficient times the natural log of the base times the derivative of the exponent times the exponential part. And for problem 11, the coefficient is the number that's to the left of that e squared. So the coefficient is 1. The base is the e. The exponent is the x squared, so the derivative of the exponent is just the derivative of x squared. I just bring the 2 out front. So I'm just taking the derivative of x squared, bringing the 2 out front, lowering the exponent down to a 1 and getting a 2x. And the exponent part is the whole function since there isn't a coefficient. So if I want to write down the derivative, usually I don't write pieces down that are equivalent to 1, but technically it's the coefficient 1 times the natural log of the base times the derivative of the exponent times, I don't need a times sign here for that times the exponent part. And because the natural log of e by hitting second and divide is equal to 1, this is really 1 times 2x times e to the x squared. I generally don't write parts that are equal to 1 as I'm finding the derivative. So if I was writing down the derivative for problem 11 on this practice test, I probably would have skipped those 2 parts and just wrote the derivative of the exponent times the exponential part. And that will work anytime you're doing a derivative of an e that doesn't have a coefficient. So that would be a completely adequate answer. And I probably wouldn't show any work. I would just write the answer down just flat out. In problem 12, there's multiplication and both factors have a letter or variable, so I need to use the product rule. And remember, the product rule is first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. So I'm going to write the first factor down, and I'll write the second factor down. I'll find their derivatives. The first factor is 2y minus 4. The second factor is e to the 5y squared. The derivative of the first, the derivative of 2y, since it's the first power term, is just the number in front of the y, which is 2. The derivative of the minus 4, because it's a constant without a letter, is 0. And the shortcut way to find the derivative of an e without a coefficient is just to the left of the function to write the derivative of the exponent. So when I go to do this derivative for the e part, the coefficient is 1, so I don't need to write it. the base is e, and the natural log of the base is equal to 1. I don't need to write it. So when I go to do the derivative of that e part, the second factor, I'm just going to take the derivative of the exponent times the exponential function itself, and I don't subtract 1 from the exponent. So the derivative of e to the 5y squared shortcutted is just the derivative of 5y squared. I go 2 times 5 is 10, lower the exponent by 1 and get a y to the first. So the derivative of 5y squared is 10y. And the function itself, the exponential piece, is e to the 5y squared. That's the shortcut way to find the derivative of an e function that doesn't have a coefficient. Now I'm going to kind of cross-multiply in some sense, maybe write some things backwards because I kind of tend to do that. So that's what I'm going to write first. The first factor times the derivative of the second. I'm going to write them backwards. So for the first factor, because it's a binomial, I'm going to put it in a parentheses. And then instead of writing the derivative of the second after the 2y minus 4, like the formula kind of calls for, just like I did a bunch of times in the videos, I'm going to write it first. It just looks better to me to have the parentheses written second, but it doesn't matter. It would be correct to write it the way that I wrote the formula. I'm going to bring down this plus sign, and then I'm going to multiply this way. And again, I think I'm going to backwards these. So first I'm supposed to write the second factor, which is e to the 5y squared. And then technically after it, I'm supposed to put the derivative of the first factor, but I'm going to put it before it. And usually when we're using the product rule, we get common factors. And between this 10 and that 2, I can factor out a 2. Probably could have factored out a 2 from that parentheses. I'll get around to that in a bit. From this 5y squared and this, well, maybe I won't even get around to it, and this e, both of them have an e to the 5y squared in common, so that's also going to be a common factor. What's going to be left, to the left of the plus sign, this y is going to be left. This 10 is going to turn into a 5, so it's going to be 5y here because of the 2 that I factored out. I took it out away from the 10. That's going to turn it into a 5. The y stays, the 2y minus 4 stays, and then after the plus sign I factored out both pieces, and if I factor out both the entire, something equivalent to the entire term here, I leave a 1 behind. I guess I'm not going to factor out that 2 there specifically because I'm going to clear the parentheses and try to simplify the inside of that parentheses that has parentheses inside of parentheses a little bit differently. So I'm going to clear this parentheses and go 5y times 2y and get 10y squared, 5y times minus 4 and get minus 20y, and then plus 1. I'm sure that's prime. I'm going to check real quickly. Do program quad, enter 10 for A, minus 20 for B, 1 for C. It has decimals, so it's prime. So this will be the best answer for problem 12. And now there is no common factor inside the parentheses of 2. If I had factored out the 2 earlier, I'd get to the same answer. My work would look a little bit different. 13 is a fraction, so I'm going to use the quotient rule. Remember, the quotient rule is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And I get a new marker out here. And for the denominator, I'm just going to write e to the 5t, e to the 2t, should I say. So my denom is going to be e to the 2t. My numerator is 5t to the 4th. And I need to do the derivative of each. For the derivative of the denom, it's an e function without a coefficient. So the quick way to do the derivative is just going to be the derivative of the exponent times the e function itself. I'm not subtracting 1 from the exponent. So the derivative of the exponent is just the derivative of 2t. The derivative of 2t is just the number in front of the t, which is 2. And then times the e function itself. So when you're doing derivatives of e's, the exponent doesn't change. For the derivative of the numerator, the derivative of 5t to the fourth, I go 4 times 5 is 20, lower the exponent by 1, and get a 20t cubed. Now I'm going to kind of do the same thing. Multiply that way, and go the derivative equals 2. I could write these in either order. I kind of like the 20t cubed first. I'm not even sure why. It doesn't matter. I have a tendency to write these things backwards, and I'm going to. But if you would have written e to the 2t times 20t cubed, it's equally correct. Just somehow I'm just used to seeing it like that. I'm going to bring down the minus sign. And then for the numerator times the derivative of the denominator, I'm going to write it probably backwards again. For the numerator, I'm going to write a 5t to the fourth. For the derivative of the denominator times 2e to the 2t. It might make it easier for you to follow if I multiply this 2 and 5 before I do my common factoring in the numerator. But I better write down my denominator of the denominator all squared. So for this numerator, this piece 20t cubed e to the 2t, I probably can't write much better. But this piece I can multiply the 2 and 5 and get 10 e to the 2t times t to the fourth. And now I probably should have written the e piece second, but it doesn't matter. Now I'm going to common factor the numerator, the orange version of the numerator. Between this 20 and that 10, I'm going to factor out a 10. Between these t's, the t to the third and t to the fourth, I factor out the smaller exponent, which is a t cubed, and there is an e to the 2t on either side of the minus sign in the numerator. So that's going to be my common factor. What's going to be left to the left of this minus sign, the 20 is going to turn into a 2. When I factor out a 10, I divide the 20 by 2 and get a 2. I factored out all three of the t's there, so there's no t left. And I factored out the e to the t, 2 to the 2t, so there's nothing left from it. So before the minus sign, the only thing left is a 2. After the minus sign, when I factored out a 10, I don't need to write anything from this 10 because I factored it out completely. The e to the 2t, I factored out completely. There were 4 t's after the minus sign. I factored out 3 of them. I'm left with a t to the first. And I like to, when I'm doing these t's and the quotient rule, or these e's and the quotient rule, should I say, instead of writing the denominator with a square, write it down twice so that the common factor that generally comes up you can cancel out. And now I have an answer that I'm going to stop with. I'm going to leave the parentheses written with the t second. You can rewrite the inside of the parentheses with the t first and factor out a -1 if that's something you like to do. But that's what I'd call probably my best answer. An alternative would be to take that numerator, write the t first and the 2 second, and then factor out a -1, and I don't have any room, but I could have made this -10t cubed times t minus 2 over e to the 2t. That seems just kind of ridiculous to do. But I could have factored out a -1 there, which would make the 10 negative, would flip the sign on the t and the 2, but that's overkill. This is what, if this was a test, this is where my key would stop. I wouldn't take the time to write the 2 minus t with the t first. 14's an ln, and remember for logarithms derivatives, the derivative, it's the coefficient times the derivative of the argument divided by the natural log of the base times the argument. And just like the E problems, in ln problems, a lot of times some of the pieces of the derivative are equal to 1. So for this particular problem, there isn't a number to the left of the ln, so that tells me that the coefficient is an implied 1. For ln, the bases are e. It's not written, but it's assumed. The argument is 3t to the 5th. And the derivative of the argument is just the derivative of 3t to the fifth. The derivative of 3t to the fifth is 5 times 3 is 15. Lower the exponent by 1, t to the fourth. There's no ln in the derivative of an ln. It's a big deal. Just like the exponent doesn't change in a derivative of an e, there's no ln in a derivative of an ln. So let me write down the derivative. I'm writing down pieces I don't need to write. The coefficient of 1 doesn't need to be written in the numerator. The derivative of the argument does need to go in the numerator. In the denominator, the natural log of the base doesn't really need to be written because the natural log of e is 1. I think I might still have that on my calculator. No, I don't. Natural log of e, second and divide to get the e, is 1. So these two pieces I probably shouldn't have written. So coefficient 1, derivative of the argument, 15t to the fourth, natural log of the base, natural log of e, which is equal to 1, over the argument 3t to the fifth. So this is really just 15t to the fourth over 3t to the fifth because the ln of e is 1. So this is really 1 times 3t to the fifth. I'm just going to reduce the fraction. I'm going to simplify by dividing 3 into 15 and getting a 5 in the numerator. And for the t's, I'm going to subtract the exponents and leave the t in the denominator because the larger exponent for the t is in the denominator. 5 minus 4 is 1, and we'll be left with a t to the first power in the denominator. And I don't need to write the exponent when the exponent is 1. It's an ln problem. It's multiplication. Both factors have an x, so I need to use the product rule. So I need to write down the first factor. First factor is x squared. The second factor is the ln of x. The derivative of the first factor is just the derivative of x squared. You just bring the 2 out front, lower the exponent by 1, you get 2x. And for the derivative of the second, I'm doing the derivative of an ln that doesn't have a coefficient. And when you're doing the derivative of an ln without a coefficient, you don't need to write the coefficient because it's a 1, and you don't need to write the ln of the base because the base is e and the ln of e is 1. So when I'm doing the derivative of an ln that doesn't have a coefficient, the derivative is just the derivative of the argument over the argument. So to do the derivative for the second factor, it's just the derivative of the argument divided by the argument. And for this particular ln, the argument is the x, and then the derivative of the argument is just the derivative of x. It's a first power term. The derivative of any first power term is just the coefficient. The coefficient of that's an implied 1. So I'm not putting the coefficient in the numerator because that's 1. I'm not putting the ln of the base because that's the base is e and the ln of e is 1. So I'm just going to say this is just 1 over x. Now I'm going to multiply, write down my derivative. So the derivative equals first factor times derivative of the second plus second factor times derivative of the first. I just feel the urge to write this backwards. So instead of writing the 2x after the ln of x, I wrote it before. These x's will cancel. The x from the denominator will cancel out one of the two x's from the numerator and leave me just an x times 1. Fraction's gone when I cancel out the denominator. This x squared turns into an x. This piece turns into a 1. This is x times 1, which is just x. And then I'm going to simplify by pulling out a common factor of x. Because on either side of the plus sign there's an x. When I factor out an x from that, I've taken it away entirely, so I need to leave a 1 behind. And after the plus sign, I just get a 2 ln of x. You can't add an ln to an integer, so I'll just leave my answer like that. I did a separate 2 2.4 part 3 with these problems, so hopefully that's kind of fresh in your mind. To do part A, to find all values of x where the tangent line is horizontal, to do this, you're going to find the derivative, set the derivative equal to 0, and solve for x. And we have to remember that e to any power equal to 0 has no solution that comes up when I'm doing the work here. So let me do the derivative. As I go to do 16a, to do the derivative, technically the derivative of an e is the coefficient times the natural log of the base times the derivative of the argument, derivative of the exponent, wrong word there, times the e function, everything but the coefficient, or times the exponential piece. Here the coefficient is 1, the base is e, 1 is not necessary to write, and the ln of e, since that equals 1, it's not necessary to write. So when I go to write down the derivative, I'm just going to take the derivative of the exponent and multiply it by the function that's given. The exponent is x squared. The derivative of x squared, you just bring the 2 out front and get a 2x. And then the e function is that. So I'm skipping the pieces that are equal to 1. So I found the derivative. Now I'm going to set the derivative equal to 0. The derivative is factored, and I have to set each factor equal to 0. I'm going to divide by 2 for the 2x and get x equal to 0. And for the e part, e to any power can't be equal to 0. That doesn't give a solution. So for part 16a, the only answer is x equal to 0. To do part B, to find an equation of a line, I need a point and a slope. So for 16b, I'm going to create a point and a slope that fit with the problem, and it's super easy to do. The x-coordinate of the point is the answer that I got for 16a, which is 0. Because I'm finding the equation of a horizontal line, horizontal lines have a slope of 0. So those two pieces come from either the algebra in part A or the wording in part A. The x-coordinate of the point comes from just the algebra. The fact that I'm finding the equation of a horizontal line tells me that the slope is 0 because horizontal lines have slopes of 0. I need to get the y-coordinate of the point, and then I'll do y minus y1 equals m times x minus x1. To get the y-coordinate, I plug in x equal to 0, not into the original function, not into the derivative, but into the original function and not the derivative. So the function before I took the derivative is e to the x squared. I'm just going to plug in 0 and get e to the 0 squared, and that's going to be equal to 1. I could do this on my calculator if I didn't know that e to the 0 squared is equal to 1. So the y-coordinate of the point is 1. You can get the answer for the equation. If a line has a slope of 0, the equation is just y equal to y-coordinate of the point. But if I wanted to not remember that, anytime I'm asked to find an equation of a line, if I have a point in the slope, I can just do the y minus y1 equals m times x minus x1. And for x1, I'm going to plug in 0. And for y1, I'm going to plug in 1. And for m, I'm going to plug in 0. So I'm going to go y minus y1, which is the 1, equals m, which is 0, times x minus 0. On the right-hand side, you get 0 because any quantity times 0 is equal to 0. And then I'm just going to add 1 to both sides. The answer to part B is just going to be y equal to 1. Anytime we're doing a horizontal line, the equation won't have an x, it will only have a y. All right, so just one more problem. And I I think this problem's harder than what's on the test in terms of the function. So when you're studying for this, make sure to study the other practice tests. Now, there's an in-class practice test and a extra practice test. The wording of the problem may be the same, but the problem itself is the function doesn't have an ln on the test. I can't almost ever think I would do that. But here, let me just do this anyways, because the idea is the same, just the algebra is a little bit harder. So this problem gives me a function. It says the cost in dollars to make X supersized candy bars is given by this function. Part A wants me to find a derivative. So I need to find the derivative of this function. And when I go to find the derivative of the function, it's a little bit harder. This piece right here doesn't have a variable. It will have a derivative of 0. This piece is an ln with a coefficient, so I need to do its derivative properly. The derivative is the coefficient times the natural log of the base times, whoops, wrong. The derivative is the coefficient times the derivative of the argument divided by the natural log of the base times the argument. Sorry, I usually just do these derivatives in my head without the formula. I don't think about the formula so much. So to do the derivative, I'm just going to do it, I'll do it down here. To do the derivative, this piece has a derivative of 0. I don't need to worry about it. For this piece, its derivative is going to be 2. And then let me figure out the other pieces. So the argument for the ln piece is x. The derivative of x is the derivative of the argument, and that derivative is just 1. So in the numerator, it goes coefficient 2 times derivative of the argument 1 divided by the natural log of the base. And in an ln, the base is assumed to be e, and the natural log of e is equal to 1, so I probably shouldn't have written that. And then times the argument x. The numerator comes out to be 2. The denominator is really 1 times x, which is just x, because the natural log of e is equal to 1. So my answer to part A is c prime of x, or the derivative of the cost function that tells me the cost of making x candy bars is 2 over x. On the test, students do really good on the evaluate questions, not so good on the interpret. So this is a cost function. If I plug a number into the cost function itself, it will tell me how much it will cost to make that many candy bars. So for cost functions, plugging a number into the original function, which is the cost function, for this problem will tell me or give me the cost of producing the total cost. How about the total cost of producing that many candy bars? That's just a cost function that has nothing to do with calculus. The derivative of a cost function is called the marginal cost function. Derivative of a profit function is a marginal profit function. So the derivative of a cost function is called the marginal cost. And maybe I can think of marginal as next. The marginal cost function, and what it estimates, it's not the total cost of all the candy bars produced, it estimates the cost of producing one more, whatever you're making. In this case, candy bars. If it wasn't, if it wasn't a candy bar function. It would be the total cost of producing hockey jerseys, I think I do often. So let me do the evaluate and interpret. Part B, I just need the original function because there's no little prime next to the 4. So I'm going to use this function and go C of 4 equals 2 times the natural log of 4 plus 0.15. I'm going to round to 2 decimals because this is the cost of candy bars, which is money. So I'm going to go 2 natural log of 4, close out my parentheses, plus 0.15. And I'm going to round that to $2.92. So this says it will cost a total of $2.92 to make, I guess, 4 candy bars. So each one costs about 70 cents or so, 70 cents, 75 cents. So that's the total cost. Basically, if I took this $2.92, divided it by 4, that costs about 73 cents per candy bar. Plugging a number into the derivative, that's what this is asking me to do. It's saying find C prime of 4. It tells me, it estimates the cost of producing the 5th candy bar in this case, because I'm doing it at 4. So I'm just going to use the derivative, which I have down here, or I have up there, and I'm going to go 2 over 4. I'm probably going to make that into a decimal, which is so strange, but I like decimals when it comes with money better than fractions. And that's going to be the same as 50 cents or $0.5. I don't know if I could squeeze this in here. Let me do it in a different color. I'll say the cost of the 5th candy bar will be about, and then whatever the answer to this is. Either I could put it with a dollar sign, probably with 2 decimals, or I could write that as a cents, half a dollar that is, which is 50 cents. I make the functions kind of easy to do the calculus with because of the functions are kind of designed so the math is easy. Sometimes the interpretations, maybe the numbers aren't really realistic, that when it costs an average of 73 cents per bar to make 4 bars, why would it only cost 50 cents to make the 5th bar? This is because if I tried to make a function that would more realistically do the cost of producing candy bars, it would be a more complex function, and it probably wouldn't make sense to ask like 4 candy bars, because no company's going to make 4 candy bars. It'd be like the cost of making 4,000, find the cost of making 4,000 candy bars, evaluate and interpret C prime of 4,000, which is the cost of making the 4,001st candy bar, I suspect. Just the algebra would be worse than we want to do. So it's going to be important on the test to be able to just march through these parts. The derivative of a cost function is a marginal cost function. One part asks you to put a number into the original, and that's just the total cost of making that many, whatever the product is. And one part asks you to plug a number into the derivative, and that's the marginal of the cost, and that's the cost of making the next. In this case, because I have a 4 there, it's the cost of making the 5th candy bar. And I always have to take a lot of points off. Students get the correct part. They get the right number, but they don't do the interpret, and I kind of take off, it's usually like 5 points for the question, and I take off 3 because the evaluate's easier than the interpret. Alright, so that should hopefully get us ready for the test. Chapter 2 is one of the harder tests. Actually, this summer I've redone most of the videos in Chapter 2, hoping that's going to make the test scores a little bit higher, but 2 and 5 are the hardest tests, so hopefully what I've done is working for you.